right. It's my pleasure to introduce John Bowditch and Steve Mokris. John and Steve from the Grid Lab are presenting on advances in digital photogrammetry and how it can be applied to game development and computer graphics. The Game Research and Immersive Design Lab, an initiative of Ohio University Scripps College of Communications, was developed by college staff and faculty to provide the Appalachian Ohio region with training, education, and opportunity to develop technical and creative skills through the use of interactive digital game technology. Welcome.
Thank you. I'm John Bowditch, Director of the Grid Lab.
I'm Steve Mokris, Technical Director of the Grid Lab.
And today we're going to be talking about technology that we're using on one of our current research projects. And we're going to be giving some demonstrations. We really don't like formal presentations, so if you have any questions, just raise your hand or shout at us or something.
When he gets going, could you set this to anything but 85 hertz? You know how to do that? We'll
Yeah.
do it in a minute. Just as he gets
Okay.
going, you
Yes.
set it to 75.
Yeah, when we switch to his, that'll be fine. So we're just going to give you a quick overview of the Grid Lab and our mission, discuss some of the research problems that we came across looking at our current project, discuss the historical use of photogrammetry. It's actually a technique that was really invented in the 15th century, but with advances in computing technology, is becoming widely used in the digital realm. Steve is going to actually demo some of our immersive cameras that we've brought, and we're going to give a quick tutorial of the different software we use and how it fits into our game development pipeline. So the Grid Lab, GRID stands for Game Research and Immersive Design Lab. We're just entering our 4th year as part of the Scripps College of Communication at Ohio University. We are our own department. So we actually serve 5 schools within our college, primarily the School of Media Arts and Studies and the School of Visual Communication. We have a digital media degree in the School of Media Arts and Studies, and that focuses on game development, computer animation, and special effects for film and video. We have some of our students here. So our research problem. We were approached by the Columbus, Ohio Police Department, specifically their Homeland Security Division, to look at a way to model the city of Columbus. Our first thoughts were, well, we'll just go to our strengths and do 3D modeling, but doing that for 60 structures, mostly skyscrapers, in the Columbus, Ohio area, wasn't really feasible. So we started looking. The biggest problems were we had many models to do, many locations and many settings. If you just look around this room, if you've ever done computer modeling before, you know that even just this room would be a huge challenge. So we got a contract to work with them. The first contract is a 24-month contract. We're about 6 months into that now, which will conclude in 2010. And what we're doing is we're using photogrammetry tools to rapidly produce models for a web-delivered simulation. And we're going to go over some of the technology we're using to make that possible. But Steve and I are pretty experimental when it comes to research, and we don't really like to just do contract production work, so we like to try out new technologies, new techniques. And it didn't take us long to find a relatively new field in computer science called photogrammetry. Okay, so what is photogrammetry? From our point of view, as far as using technology to capture visual images, photogrammetry really got it started around the beginning of photography itself, so mid-1800s. And it was primarily used at the time for topography and cartography purposes. So essentially, it uses a process of triangulation, right? So we would have more than one camera, generally 2 or 3 shots are a minimum. And basically what we're trying to do is just we're trying to get multiple perspectives on a 3-dimensional object, right? We can actually use photogrammetry to extract 3D models from just one image, although it's very hard, and it's really hard to get a concept of the depth.
Since there's no depth information.
Yeah, so I mean,
you have to generate that
I mean,
entirely yourself.
if you're extracting a model from a 2D image that is common to you, right? If it's an iMac, you know how thick an iMac is. That might be okay because you can guess that information. But really, I mean, the roots date back all the way to the 15th century. You have several Renaissance painters that discovered the power of perspective, including Leonardo da Vinci and one of my favorites, Vermeer. And so they basically understood the concepts of the line of sight and were able to determine perspective and make it look like it's 3-dimensional on a flat surface. So, for most of the 20th century, it was still a non-digital craft, primarily still used for topography and cartography. But with computers becoming much smarter and much more user-friendly, there's a lot of mainstream tools out there, but the process is still not mainstream. And basically because of price. Would you say that's accurate? And we'll go over some of the barriers to entry in this field. So here's an example of perspective. Steve, do you want to explain this?
Go ahead. I'm not
Well,
familiar with this particular.
this is actually a painting from the late 19th century. And so, maybe if I can walk over here. Can you hear me if I just talk like this? So you see here, this is actually probably the best image. You have lines drawn. You all did this probably in like an early art class, even like in high school, right? Where you can actually see where a camera might be here or down there, and you're able to interpret what a 3-dimensional object would look like, even though that's flat, right? So that's what we're basically telling the computer to do, to help us with. So we get to digital photogrammetry. This is actually a shot from one of the oldest buildings at our university, actually the oldest building at our university, called Cutler Hall. And this is actually made up of just 2 images, 2 scans, and we're going to go over that more in detail. I just wanted to kind of give you an idea of where we're going with this. So the left image is a wireframe image, and the right side is a textured model. So Steve's going to talk a little bit about our 2 types of immersive cameras and some of the barriers that come with each.
Okay.
So,
On the left here is the Panoscan Mark III. This is a boutique item, the sort of item you'd need to take out a second mortgage to purchase. This thing, it's basically like a flatbed scanner. It has a single row of CCD pixels to detect the image. And this thing, on the base, there is a motor which rotates it around 360 degrees. The lens is a 22.5 millimeter fisheye lens, which gets slightly above 180 degrees in the vertical direction. So we squeeze 180 degrees into the vertical strip and then get vertical strips rotating around in a circle. Initially, we started out with these funded by the grant. We have that one right there in the center, and I'll show you a demo of that in a minute. Some drawbacks to this were obviously the expense. Additionally, it needs to be very stable in order for it to scan without the lines jumping up and down. So we've had some stability issues with that. It takes a long time to do a high-resolution scan since it is only scanning one line at a time. And depending on the shutter speed, you might get between 60 and 100 lines per second. So it takes several minutes to rotate around the room. So we were looking for less expensive, more portable, user-friendly alternatives. And we noticed that Canon has a nice SLR camera. And we discovered that by using an extreme fisheye lens for this, one that can get us a 180 by 180 photograph, we can then mount this camera on a mount kind of similar to the rotating one, but one that we manually rotate. And the mount has notches in it, so we can rotate it at preset intervals. Then we can take a series of snapshots, and using the open source project Hugin, we can stitch those together into an image very similar to what the Panascan creates and the digital SLR kit, including lens and a really nice tripod for it, comes in under $2,000.
Yeah, which is about a 20th the cost of the other one. So I mean, but there's advantages and disadvantages to both, and we're going to go over that.
Yep.
Steve's going to do a Panda scan demo first. Since it's kind of a small crowd, and if you'd like to get closer, please do so. If you have questions afterwards or you want to come up and see it, I can demo it after the presentation. Did not see it.
One of these is an input and one is an output.
Oh.
We plug them both into the input. One moment, please. Yeah. Okay. Okay. Main screen turn on. Yes. Okay. Maybe.
Well, while he's setting that up, just some more information about the camera. This particular lens is 22.5 millimeters. And we're actually going to do about a 380-degree scan. It's better to overscan, so you can line it up later. And since it overscans vertically, we actually need to match up the floor and the ceiling, because it will pick up even the tripod in the scan. If it's really designed for the camera operator to be down at the base. There's like a little plate for the MacBook, but even that person will be picked up in the scan. So it's a little too much in some ways. All right.
Okay. So prior to starting, we did a test scan. I'll go ahead and initiate a new scan here. So yeah, the Better Light is the manufacturer of the CCD array in the camera device here, and then it's resold by another company that integrates the CCD array into the whole motorized apparatus. Yeah, let's do a full scan here. This says it will take 3 minutes, 21 seconds.
And we can use a light meter to gauge the amount of light to set the lens. The lens is manual, but what we really just do is do a pre-scan in a room. In this case, these settings only take 25 seconds, so we can determine really quickly how the image looks. We could also make modifications, and it'll simulate what it will look like if we change the ISO or the line time. So when it gets close to you, be very still.
That makes it look really funny if you move, especially if you move vertically while it's scanning.
Yeah. But you can have a lot of fun artistically with it. Steve and I were doing some early tests where we wanted to play with removing multiple people from an image, and it was just he and I. And so we would start the camera, we'd let it scan us, then we'd run around the opposite direction and get back in the shot, and pose differently. And so we ended up getting the shot 4 or 5 times, just
At least.
through some hustle.
Yep.
And You can see the vertical bar going across the screen there. It's not actually updating the scan on the screen. That's actually the pre-scanned image that I took before this presentation started, so you're not actually seeing yourself scanned in real time.
A deficiency in the software. We're working with the vendor to correct, hopefully.
Do you want to talk about file size with these?
Yeah,
Pixel resolution?
So right now, we're operating at a 50% resolution. If we crank that up to 100, it'll take roughly double the amount of time, or quadruple. I don't remember exactly how that scales, but and adjusting the line time, the shutter speed for every vertical segment also affects the scan time. So we've had some scans that have taken up to 20 minutes or so if we're doing a dark room at full resolution. When we do a full resolution scan, the output ends up being around like 8,000 pixels by 4,000, I think.
Yeah.
The CCD array in this camera scans at more than 8 bits per channel, so I think it does 14 bits per channel. So when that's encoded in TIFF format, a single scan consumes about 1.5 gigabytes of storage.
So it's huge, right? And the final output of this is a web-delivered 3D game. So obviously, in a room this size, we would probably end up doing probably between 6 and 10 scans to get the perspective that we needed, right? So just to do this room, if the textures are, over 15 gigs, that's not going to be very web-ready.
Okay, we are almost done here.
So this scan is actually a TIFF file. It's not a raw file, and it's compressed to about 52 megabytes. That's still not very web ready, and we'll show how we actually get that down to a 3D textured model under a megabyte.
That is still intelligible, oddly enough. The scanner is rewinding. Cool. We will save this to the desktop.
And you can use multiple lenses on that camera. You can anything that's not fisheye will become like it'll look like a cylinder, right? So if you wanted to do mountainside scans, or like if you're down in a valley and you wanted to scan around it, you could use a telephoto lens, but you're not going to get top and bottom.
Tell what's going on there.
It's a little dark in here.
Yeah.
And we actually have a light rig that sits right above where the motor is, and will light with the camera as it moves around.
So this is at full resolution here. We can see pretty huge amounts of detail. That's what happens if you move.
Whoa. For our purposes, since we care more about the structure than the people that would be in the shot, even like the chairs, since these chairs most likely aren't always configured like this, we would probably end up removing them. Either we'd create a texture that erased the floor. Whoa, go back and, or just made a constant texture across the floor. It's much easier for us to build a mesh of a chair and place them wherever we want, and let the let the person driving the simulation determine how to interact with them. You also notice some vertical stripes. It's one of the challenges we're still working out. Whenever there's a point light or directional light, you generally get like a streak. And so we're working on methods to reduce that. Actually, 2 of these 3 students up here work on the Ivan project. That's what this project's called. And in a typical 8-hour work shift with 2 camera rigs, we can do about 200 scans in a facility, which is about 2.5 minutes per scan. So we move quickly. We don't want to go back and have to touch up a lot of images.
Yeah. Okay, so yeah, this is our base image here. Let's see. The resolution, yeah, this is about half resolution, so 3,000 by 6,052. So actually it does 12,000 horizontally at full resolution. I will save the brighter version, and now we can, one quick way to preview this is as a QuickTime VR movie. So we can export that, and someone who downloads that can, or within a web browser, can navigate inside of it and scan around. So I'll demonstrate how to do that in a minute. First of all, I mentioned earlier that the lens we're using gets slightly above 180 degrees in the vertical direction. So we need to correct for that because we want an equirectangular image, one that scans an entire 360 degrees along the horizon, the yaw movement, and 180 degrees from top to bottom in the pitch direction. So since we have slightly more than 180 degrees vertically and slightly more than 360 degrees horizontally, so we need to then crop this. So we got this little utility here.
Yeah, and surprisingly, the Panda rigs right now only run on Apple computers. Even though I think most of the software, with the exception of the proprietary stuff that came with the camera, is cross-platform.
Okay, so I need to copy something from the server. Just realized. Okay, so this view here allows us to adjust the horizontal seam. So let's see. I think by reducing the width, yeah, reducing the width, we can keep these sections to align. That's a little closer, and then we can zoom in. It's easiest to see where the edge is at the edge of this the chandeliers hanging from the ceiling here. So make that a little smaller and try to get that line. That's too small. That's not bad. Does that line up all the way across the image?
Yeah, generally, we set up the camera to scan first on a straight line or a corner, or we can match it up easily.
Yep. Okay, that looks good. Then now we can crop the left, or the top and the bottom. We are, so let's see, this is kind of, in order to calibrate this properly, you'd want to have more or less a grid set up both above and below the camera. So some fancy hotel carpet pattern works pretty well. This one's a little too fancy. And like the typical like office lighting ceilings where you have the like 4 foot by 2 foot tiles. Then you can tell what is a straight line and what is curved. So we notice up here, this is a little curved and this is a lot of curved. So we're going to reduce the height a bit to compensate for that. That looks a little better. And on the bottom here, yeah, the carpet is still coming in at not quite the same angle. That's a little better, I think. Yeah, we'll go with that for now. Radial color correction, lens distortion correction, 22 millimeter, equirectangular, wrap horizontally, don't create a movie. Okay. Export. Where are we? NOTACON.
And one of the neat things, since in production, we would scan this room multiple times in a series of lines. We'd basically kind of create a grid and go across that. You could kind of see in the bottom, you saw like a disc shape. That was the camera it picked up. If we do multiple scans and we overlay them, they actually will move out the camera. We'd only have to remove the camera once in the entire room. So it's pretty handy.
Yeah. So this is the cropped image. It doesn't really look much different because we just removed edges on the top and the right and left. Okay, now we can take that into cubic converter here and build a QuickTime VR movie out of that. equirectangular, cube faces, convert. So it is now mapping the rectangular, or the equirectangular spherical capture into a series of cube faces, so that when QuickTime VR displays this, all it has to do is render a set of 8 or 6 sides for 6 quads for a cube. And now we get a fairly realistic perspective view of the room from here. And unlike previously when I was just scrolling around in the image, we actually see it kind of warping around at the edges, which gives us a little more realistic perspective. So we got that. We can then export this.
So yeah, this is a QuickTime VR image that can be embedded in the HTML page.
Okay, and yeah, here's the QuickTime VR version, and look at that. And yeah, somehow you can, yeah. QuickTime VR is not very exciting. The exciting stuff is what we can do after that. So should I demonstrate the SLR now?
Sure, yeah.
Okay.
I think we have time for that.
So,
Yeah, so that's just one possible output of this, a QuickTime VR.
Yeah.
We're going to show another solution here.
okay, so yeah, that took a while, but what we ended up with at the end was a single equirectangular image. What we're going to do here is take this camera, an SLR with the 180-degree fisheye, and let's see, this needs to not go on like that. Okay. Maybe we can kind of, this isn't going to be very precise. Okay, so yeah, the camera rotates around here. We've got the focal point roughly at the center so that we don't experience parallax error. And then it snaps into position at 6 locations around the 360 degrees. So turn on the camera. I'll stand right here and take a series of photos. How do you use this camera?
This is kind of a upper-end consumer camera you could pick up anywhere. I think we got these off Amazon.
Yeah, it's $400 or so. And now we're back home. So yeah, that's all we need to do there. The advantage of this is we don't have a laptop hooked up. We don't have that whole gigantic camera that gets all tangled up. Very easy, portable. When you're on the road, you can take this with you. It takes no space whatsoever, and you can quickly shoot a couple shots, pack up, leave. So great for those situations. However, once you've shot the photographs, it requires a bit more post-production work because then you need to stitch together all of those images. So I will connect this here, download the images, and give a quick demo of using Hugin to stitch these together.
And Hugin's free, cross-platform. And it is Hugin. Steve found a YouTube video like 3/4 of the way through where they said it in Swedish.
This should be downloading the photos, maybe. Desktop.
Excuse me, I have a quick question.
Sure.
The Cubic converter program that you guys brought up earlier, is
Uh-huh.
that something that's proprietary, open source, or be available?
We had to license it, and I'm pretty sure it's
Yeah,
proprietary
that
to
is
the
proprietary
camera.
software. There are open source equivalents. I don't remember offhand what they are, though, but we can look that up.
Yeah, and I mean, you could use VRWorks, which is it's kind of an old product now, but it's a few $100s, I think.
Okay, so this is what the, shoot. Exposure. That's not looking right. Okay, that looks decent. Yeah, here's what the room looks like. One photograph. So a lot of the CCD space is wasted here, so we're looking at ways to increase the amount, or the projection space taken up on the CCD. We've tried using like macro lens extenders, but haven't had very much success with that yet. So we're open to suggestions. So we've got 6 of these images here, and now we can take them into Hugin and stitch them. So yeah, this program is free open source. Up there, desktop, see. Okay. So we're going to pick these 6 images. The lens is cylindrical panoramic, focal length 4.5 millimeters. No, just 4.5 millimeters.
It's, yeah, try that middle one.
Yeah,
The
it's
circular,
circular for try.
yeah.
My bad. 4.5. Yeah, that works better. Focal length multiplier 1.41. Okay, now, actually, before we do that, there was a lot of black space on the edges. We need to eliminate that black space and make it alpha transparent. So I've prepared a little application here that will let us do that if Finder cooperates. Come on. Okay.
So it's obviously a lot cheaper to use this solution, but there's a lot more prep per 360-degree scan.
Yeah. Yeah. So once you've shot the images, then you can run them through this little app that I wrote here that it crops them down and it adds an alpha mask to the image and converts it to a PNG file. So then we can feed the alpha transparent images into Hugin, and it will properly deal with the transparent areas. Why is this so slow? 2 kilobytes? Serious?
Do you want to switch projectors so we can go into
Sure, yeah, let's come back to this.
photogrammetry real quick and then come back to that? It's probably going to take the rest of the night to download 1.5 megabytes.
There we go.
Okay, so for photogrammetry, we use a software application that wasn't really developed by Autodesk, but is now owned by Autodesk, called Image Modeler. Used to be Virtools, which was owned by a company, Virtools. So we have a video of this. This is kind of a time-consuming process, so we kind of consolidated a little bit. So essentially, this is a room from Ohio University. We have 4 scans within that room, represented at the bottom. And those blue dots with the text are essentially locator nodes. What we do is we will usually look for corners or doors that are square. We know the dimensions of them, and that show up in every camera shot. So we will place points in the corner in each camera's perspective, and the computers will process how to match those up. In this case, we're just building a cube that will represent the dimensions of the chair. And here it is in just a bland shader. So this is a process of creating a mesh from this. The nice thing is we can export this model as one model, take the four scans, export it as one model with one texture file. It lays out the UV images together for us, which is very difficult to do if you model from scratch. Just very time consuming. So this is Image Modeler. Up until about 2 months ago was Windows only. This is actually on the Mac version, which just came out. Unfortunately, there's no educational license, so right now this software runs for about $1,000 a license. but it's pretty intuitive and it's really simple to learn. Okay, so from here, you can actually export this to several different modeling applications, all of them Polysoup. We use Maya, that's what we teach in our classes. And so from this is actually a mesh that was created from a single scan in a room in that same building. So from one two-dimensional image, we were able to gather this much data and build a three-dimensional wireframe. So this is it as a wireframe with just a simple Lambert shader and then with the textures applied. All right, so we're outside it right now. That's why the insides are, you can look through the walls. But if you get down in this space, you can see all the different sides. Now this image is really still rough, and we wouldn't ship it like this. We would go through and we would remove the camera tripod and any different artifacts or chairs that bleed into the carpet texture that we want to get rid of. And that's very simple. We just take this UV mapped image into Photoshop and touch it up however we need to. From the time of scan to when we have it complete, it's about a 60 to 75 minute process per image, which is pretty time consuming because Steve and I have other projects going on. So thankfully we have about 20 students on the project that help out and do a lot of the more artistic work and just help process the image and do the models. So it's really good portfolio material for them, for the undergraduates, and it's good research material for our grad students. Unfortunately, most of the structures we're doing in Columbus are classified areas, so we can't let them use them in their portfolios when they're done. So we're looking for just kind of unique spaces that we can scan for practice and for portfolio purposes. So we've done 2 buildings now, Cutler Hall, which turns 200 years old in, I think, about 5 or 6 years. And we did a new medical facility in Chillicothe that's a very modern building with lots of glass and lots of reflective surfaces. So that was another challenge in itself. Do you have that set up, Steve?
Yep, this is ready. Okay, so going back to the images from the digital SLR, we now have this masking program down here. If the display comes on. Yes, okay. Okay, so we've got these 6 masked images. I'll open up one of these. So the original image is here. We've got all this black area, and then the masked area, it's showing transparent as gray right now. I can adjust that. So the black areas are transparent, and then we have a sort of gradient that goes in toward the center here. We noticed that with this particular, with the lens that we're using on this camera, when we get toward the very edges, we notice significant color, like chromatic aberrations, color shifts going on, and it loses focus. So by increasing the alpha transparency of the image, we can tell Hugin that that part of the image is not important, and it places a lower weight on it when calculating which parts of the image to include in the composite image. So we go back into Hugin. I will not load those images. I'll make a new thing here. Okay. Thank you.
Hey, it's open source.
It's still under development. Load images. So load the 6 masked images. Circular fisheye. Focal length 4.5, 1.41, no, 2.41, 2.5. Okay, 2.16 roughly gives us about 180 degrees horizontal field of vision. I have to do that again. 2.16. Okay. Good, we got that loaded. Now, Hugon comes bundled with a separate application called AutoPano, which will automatically analyze the set of images that you send into it, find distinct points on the images, and attempt to match these points across the different images. So now we'll run through the alignment process. So it starts by looking at each image. It scales it down to a more reasonable resolution. It didn't find any key points in that image. That's bad. Why is it not finding key points? Okay. Well, we can do this live. Maybe. Okay. If the automatic feature extraction doesn't work, I think it's probably a configuration error. I just set the software up on this laptop last night or this morning or sometime. So we can pick points on here that are common, that are seen in both images. So we're looking at, okay, the laptop is visible in both images, though not very visible on the screen. We can pick an edge of the laptop, pick an edge of the laptop over on this image, and tell it to correlate those two. Then we can do likewise with a few more points.
So it's the same concept of image modeler, just a little different. Obviously much cheaper.
With the image modeler,
Uh-huh.
you guys did that thing with the people line.
Uh-huh.
Was that something that was part of the image modeler itself, or was that something else?
You mean the wireframe?
Yeah.
Yeah, it creates the edges in Image Modeler, but then we just exported it to Maya. It exports to Maya and 3D Studio Max because they're both Autodesk products now. You can also export it to Blender and some other, I think Cinema 4D, some other applications.
Okay. When you're doing this for real, you would want to add as many control points as possible. I'm just going to add 2 per image, which is probably going to look like crap, but it might actually give us a usable image. Add. One more. This chair right there. Chair.
Yeah, so like if we were going to do multiple scans in this room, generally we do, we kind of imagine like a 10-foot by 10-foot grid. 10 feet's pretty good distance. It really depends on the ceiling height. Actually, the more wide open the space is, the less scans you have to do. And the Panda scan is actually really great for that. So we would maybe start at a door or a place where we can kind of determine as an origin, and then move 10 feet from there. Either step it off or use a measuring tape. Usually the floor either has tiles that are 12 inches, or we can just count ceiling tiles that are 4 feet by 2 feet. So, I mean, it doesn't have to be too exact because we're going to be moving around in image model later. We just have to, I think coverage is more important than, making sure you got like equal distance apart.
So how do you guys, you showed how to take the, a single 2D image and then find the corners and,
Mm-hmm.
when you have multiple images, how does it combine into a single 3D?
Yeah, I mean, multiple images really, we do it per room, right? So we finish a room in an image modeler, then we export it to Maya, and then in Maya, we actually line up and connect the rooms. And from there, I mean, we can, generally what we do is we do about 4 rooms as one model, or the equivalent of about 100 feet. And that's primarily because of drawing distance in our game engine. The game engine we use is Unity 3D, which up until a month ago was only Mac. Was only a Mac software piece. Now it's both Mac and Windows. Really cool game engine. It's what we teach in. But the neat part about it is we can actually export it as a 3D web-based game with all it requires is a free plugin from Unity. highly suggest you check out Unity if you're at all interested in 3D game development. You can also do 2D game development in it, so kind of like isometric platformers, and they have an iPhone plugin, so you can export your games to iPhone. These 3 students are all experiencing Unity this quarter, so they can probably answer some questions as well. Yes? Yeah.
Or the shadowed surfaces?
Those are more difficult, especially like mirrors, I think, are the worst, obviously, because you kind of get like a feedback effect. But I don't know, generally, we're still experimenting with that. One option, like all windows will reflect. So we've been playing with like skyboxes, like just removing the windows altogether and putting a skybox on the outside that we walk around the building and just take with regular SLR.
Yeah, and then we can take those multiple images shot with the SLR and use Hugin to automatically stitch them together and produce a skybox for us.
Yeah, and another problem is like lining up verts. Like if that camera moves just a hair, the models will not line up correctly. And plus, I mean, if you put a micrometer up to like a laser micrometer up to like any surface, no construction worker is good enough to build like square rooms, like perfect square rooms. So we have to fudge that a little bit to get it all, to make sure there's no light gaps or just holes in the game, because that can really dog performance.
We could fall through the floor.
Do you want to switch back real quick, and I'll just go through the last few slides, and then we can bring that.
This is done, actually.
Oh, it's done. Okay, good.
Okay, so in Hugin, I placed a bunch of control points. I then ran the auto analyzer that correlated the control points and produced the 3-dimensional mappings of where those images should go in 3D space to produce a spherical image, and then I stitched them together. So let's see what that looked like. Here's the output. Oops. Test. And we'll make that brighter.
So 6 images now stitched together.
Into a single image.
Very similar to what we did with the Panda scan camera. From here, we can take it into Image Modeler, do the photogrammetry work, extract a 3D model, and put it into a game engine.
Yeah, so
Pretty decent quality, too.
that actually didn't turn out too bad for the couple of control points I put. Actually, that's not cool. Yeah, so the computer does a much better job picking control points than most people.
Yeah.
So when that works, it's very helpful, and it speeds up the process a lot. So basically, it's fully automated, and within about 5 minutes of post-processing work, you can get a perfectly stitched final image out from shooting just 6 photos with a spherical lens.
Yeah, so we're still acquiring more camera kits, but the goal is to have 2 PandaScan rigs. We have both of those now. And then 6 of the digital SLR kits. So 8 people scanning at one time. And then have several, just people like image editors in the field, basically making sure that all 6 images are, there's no focus issues or anything like that. And we'll start stitching them in the field. And start uploading them from there. Because obviously, it would be kind of hard to determine which images go with which in the end if you waited, especially if you have to retake one and remove another. So why this is great for game development? Well, very, very low poly count. That image I brought up in Maya, I think, was only about 50 polys. Basically because we're dealing in cubic surfaces. And so if we scan on the PandaScan full resolution raw, the image is 1.5 gigabytes. It's useless, really. And actually, most of the software apps we use crash or won't even accept an image that high. So they're useless. So generally, the compressed files we get from the PandaScan are about 50 megabytes. Maybe between 50 and 75 megabytes. When we take them into Image Modeler to export them as Maya models, we get them down under 1 megabyte. Generally, I think I think that building we showed with texture was about 200 kilobytes, so it's nothing really, and for game models. So we've solved the hurdle of a lot of graphics and a lot of meshes that we need for this project. And part of it is, we have really good software tools. We have a really great game engine, Unity 3D. I highly recommend you check it out. The image quality is improving with further tests, new software pieces that we find, like Hugin. Hugin was a big find for us, especially since it was free. And game engines are improving. That technology is improving. You can do more with it. For example, we can export it to a 3D game in a web browser that looks way better than Second Life, right? So everything looks way better than Second Life, but. So game engines are, becoming significant. I would imagine that by the end of this project, we'll look at porting it to a mobile app, such as the iPhone or Android system or something. Do you want to talk about the technology cons?
Okay. In the case of the digital SLR, initially we just had a tripod, and we were rotating the tripod around, and we discovered that the point around which the camera was rotating was not the same as the focal point of the camera. So what happened is the head of the camera is moving, and we get parallax error. So things that are, when you're moving, things that are close by move more than, visually they move more than when they are far away. So the images thus do not line up. So by taking the little adapter that's on the top there, the horizontal bar, we can scoot the camera across so that to align it exactly to rotate around the focal point of the lens. That's basically done by trial and error. You shoot a series of photographs and do a kind of binary search to land on the right parallax-free region. We ended up doing a couple dozen shots to figure that out, I think. Let's see. Digital SLRs end up being a lot faster for on-site work, which in the case of the scanning we're doing in Columbus is very important because we need to drive from Athens up to Columbus, do the scans in one day, go back. We are working in areas that are in use, so we need to get in and get out as quickly as we can. So the digital SLRs are going to be really handy for that. So portability is great, and having more of them so we can do more work in parallel is great. Expense. The lens alone for the digital SLR system costs about $900, and that's the largest expense in that case. There still is a pretty significant expense if you want to get a decent spherical fisheye lens. Software learning curve. In order to build meshes, you need to be fluent with Maya and Image Modeler. To stitch, you need to be fluent with Hugin and remember to save frequently. Lack of advanced research.
Yeah, I mean, it's a really new area, especially in academia. So there isn't many publications out there.
One major point of interest is taking the image modeler aspect of this, like taking, once you've got the spherical image, to automatically extract 3D meshes, or once you have multiple spherical images, you can correlate those, and using fairly recently developed algorithms demonstrated at recent SIGGRAPH conferences, there are some techniques now that will automatically build 3D meshes from multiple spherical scans, which also will greatly speed up our process. But it's going to be a couple of years, at least, till that is production ready.
Yeah, and it's definitely not game friendly because
it can be tuned to be game friendly, but
yeah, it produces really high polycount images.
Yep.
Like, for example, I did like one of those kind of boomerang shaped conference phones, and I think it was like 15,000 polygons.
Yep.
Which, that's death in a game. But
yep.
Here's our contact information if you have any questions. If you'd like to see the technology after the presentation, please come up. And if you're interested in the software we use, the hardware and software, here's a list of everything. I think the only thing we didn't show due to time was Unity 3D, and the tripods we use are just made by Gitzo, which is a Bogan brand now. So are there any questions? Yes.
Most of this seemed to be indoor closed area photography. Has there been any outdoor? And do you have any issues with depth of field?
We scan everything at infinity, so the depth of field issue is not too much of an issue. Outside, the only real problems we run into is sometimes we can't find straight edges to line up points. But we have done some images in the parking lot outside the grid lab, and there doesn't seem to be any notable issues. Do you have anything to add to that?
Yeah, the exterior images so far we've done have worked out well. For this project in particular, we've been focusing on the inside because the project that we've been commissioned for is to help first responders navigate through buildings and like figure out what to do in the event that nobody can see what's going on because the building is flooded with smoke or something. Yeah, eventually we're looking at possibly doing exterior modeling of the Columbus downtown area.
Yeah. So, I mean, this technology would not be great for extracting for a tree mesh, for example, because at this point it's just way too complex of a shape. But maybe by the time this project concludes, there'll be some better technology out there for us to try.
I just wondered, is 6 images kind of a sweet spot you found on the cost benefit? You know, the more images you take, the less benefit you get?
Yeah, 6 images, we just basically put it at 60-degree increments, which I think is the lowest you can go on that.
On this particular panoramic head, yes. Yeah, 6 is what we determined to be the optimal number. If we go fewer than that, then there's not enough overlap, and it's hard to find points to link the 2 images. If we go more than that, then we just have too much redundancy, and it takes longer to shoot.
Yeah.
So,
and we should
that works out pretty well.
note that mount is it Nodal Ninja brand? Is
Yeah,
that,
Nodal Ninja.
Yeah, Nodal Ninja, NODAL Ninja. It's about $200, I think.
Yep.
So. Any other questions? Yes.
When you took the images and put it into Image Modeler, was that 3D image automatically created from the images, or was it manually?
Yeah. So the question is like when we took the image into Image Modeler, was a 3D mesh automatically extracted, or was there like some manual work that had to go into it? We have to you have to line up the cameras, similar to what Steve showed in Hugin, or when he was like lining up the points on the MacBook. We have to tell the computer that this pixel represents the corner of this door. And we do that for every scan. And then, we do this for about 4 or 5 different intersecting points. And then after that point, we tell the computer to go ahead and process it. And, from that point on, it's completely automatic. Often the depth of the mesh is sometimes off, and so that's somewhat of a manual process, but that can be done in Maya. It's relatively simplistic. Are there any other questions?
Yes, is that process the same, the one that you did in Image Modeler, is that the same process as the one where you match it to control points?
Yeah, it's very similar. Hugin really only gets the images to the point where the Panda scan got us, right? So like this one big panoramic image. From there, they would both have to go into Image Modeler, all of the different perspectives so that we can match up the points and then extract the mesh.
Do you know if the Image Modeler programs using the SIFT algorithm as well?
I don't know.
Using what?
Which algorithm?
The SIFT algorithm?
I don't think Image Modeler is using that algorithm, but yeah, Hugin and the auto panel integration does make use of that when it works.
Yeah.
But yeah,
Image
the Image Modeler
Modeler
is a lot more manual,
Yeah,
and it just provides a really convenient interface for manually placing the control points and then auto-correlating and aligning the images, and then allowing you to build simple 3D meshes to map the textures to.
Yeah, and it's kind of it's really kind of a bastard app. Autodesk buys a lot of stuff, right? And they don't really, if somebody's from Autodesk, I apologize because I like your stuff, but they don't really enhance them very quickly. It takes a while for them to kind of work out all of the different bugs, and make
porting
the
it to
features
Mac was
common.
a big step.
What's that?
Porting it to Mac was a big step, though.
Yeah, right. So I mean, I think Image Modeler was actually it was actually made up of 3 separate apps, most of it being Virtuals. But there's still some obvious issues with the software that they have to overcome. I mean, they've owned Maya and 3D Studio now for 3 or 4 years, and yet you can't work between the 2 applications. So, okay, thank you.